Welcome back, friends, for a fresh lecture which incorporates Ampere's circuital law, integral B dot dl is equal to mu naught I, which we introduced in the last meeting. And today we'll talk about solenoids and toroids. Okay, which are solenoids. Solenoid is a cylindrical thing where we can wind wire, flexible wire like this. Okay, very close wires that we can draw, right, and which we can wind on a cylindrical surface. Of course, it is a hollow cylinder, okay, and we find that, for example, if the current comes like this, then the other side goes like this, etc., and comes back and comes back and comes back, etc., etc. So there is a helical kind of a winding which occurs. The winding that I have shown over here is quite, the wires are shown to be apart from each other, okay. And while this is the direction of the magnetic field, okay, and you can see that inside the magnetic lines of field which I have shown, they are equidistant from each other. This is the section of the solenoid, okay. And if I have an Amperian loop which I have shown over here, then this is not going to be very effective for us, okay. And the magnetic field at a point outside the solenoid is approximately equal to 0, okay. There is no magnetic field due to the solenoid. There may be magnetic field due to the Earth's magnet. Well, I have not been able to draw it properly. You can look into the textbooks for proper drawings, and where you can make your own drawings, and what I am saying, you can just subscribe to that, okay. Now I have shown this is the wire is coming outside, and here the wire is going in, and they are very close together, so close that the wire has to be enameled. Enameled means it is on the wire we make a surface of insulators so that they are separated from each other, insulated from each other. Okay. So this is what I have shown over here also. The drawing is poor, okay, coming out, going in, coming out, going in, coming out, going in, and this is the magnetic field which I have shown this, and you can see that at the ends there is a kind of a fringing effect, okay. That means the lines of field, they go away from each other, okay. This is the same thing has been shown over here also. Lines of field are diverging from each other, okay. Now the whole thing has been drawn over here. The dots mean the wire is coming out, and the cross means that the wire is going in. So there is a current which you can see, and we just take, instead of a circular Amperian loop, we take a rectangular loop, part of which is inside the solenoid and part of which is outside the solenoid, okay. Now this is a B, C, D, A. Okay, this is the loop, the Amperian loop that we are going to take into consideration. Now, the contribution of the part CD to integral B dot dl, that contribution is equal to 0, because between the point C and D we say that the value of B is equal to 0. For BC and DA, either the value of B is equal to 0 or the component of the field along these lines BC and DA, that is equal to 0. The only effective thing is A to B. So the effective length of the Amperian loop that we have chosen for our discussion, this turns out to be equal to AB, which is taken as small h. Okay, no problem. Now we apply the Ampere's Circuital law. This is contour integration. B dot dl over the whole contour, this will become equal to, here the magnetic field is supposed to be the same everywhere, and this magnetic field we take as B into H. A to B is equal to H plus 0 plus 0 plus 0, and this is equal to BH. Now, if n is the number of turns between A to B, that is in the length H that we have, n is the number of turns, then the total current is equal to n into I. So from this relation we will get mu naught, and now the total current becomes equal to mu naught Ni. Okay. So from this relation I can write mu naught n upon h into I, which is equal to mu naught Ni, where n is the number of turns of the wire per unit length. Now what has happened? What has happened is that by using this long straight solenoid, within the confines of the solenoid inside, we have been able to arrest magnetic field. There is a magnetic field which is present over there. Now I am just asking you to recall that we derived this expression half epsilon naught E square, which was the energy density of the electric field. In a similar fashion, we will come to know, I am not going to derive that, but we will learn that there is a half into, instead of epsilon naught I write 1 upon mu naught, B square, which is B square upon 2 mu naught, and that is the energy density of the magnetic field. So all fields, they have an associated energy density, and so has the magnetic field. Now we are going to talk about our other friend, toroid. You see that solenoids and toroids are the equipments that generate magnetic field. For example, in the television arrangement, we need a magnetic field, and that magnetic field is provided by a solenoid. But in synchrotron, high magnetic field is required. Synchrotron is a device just like cyclotron, and there both the solenoid and the toroid, they are used to obtain this very high magnetic field, which is desired in the case of synchrotron. Okay. So this arrangement is also a kind of this thing that provides, when we'll talk further about the alternating currents, then this has an what is it called, an L associated with it. Okay, that is of course. So that is called inductance. But it may come to your mind that the kind of arrangement that I am telling you, that the wire is wound like this is also happens in the case of wire wound resistors. So you can say that if this equipment, the straight solenoid, it has got an inductance associated with it, then the answer is, and is it that in the wire wound resistances also there is this thing? Then the answer is no. Wire wound resistances that you find in resistance boxes, they don't have an inductance because they are wound with, in the sense that we take two wires together, okay, and then we wind. So in one wire the current is in clockwise direction, in the other wire it is anti-clockwise direction, and therefore there is no magnetic field. Are the magnetic fields which are generated by each kind of turn, that is cancelled by the other turn. Okay, so I am going to tell you about the toroid. So next item is toroid, and toroid is a hollow circular ring on which a large number of turns of wire are closely wound. Okay, so this is a kind of a ring just like this bicycle tube, okay, an inflated bicycle tube, and on that you wind the wires closely each other. I have not been able to draw it properly. Anyway, there is a current which enters in it, and after traveling the whole length of this toroid, it returns over here. Okay, I have tried to show it. Of course, you will have occasion to see all these two drawings which have been drawn very badly. That will appear on your screen from as copied from book, where a professional artist has done things. The magnetic field is confined to within, okay, the inside of the tube, the hollow circular ring which constitutes our toroid. So field is here, and the wires are going around. Okay. The number of turns over the whole thing is capital N. And if I take the length of the toroid over here, then we'll have the number of turns per unit length, which is equal to n upon 2 pi r, where r is inside, is taken as small n. Now, I've just shown you 2 points P and Q. These points, if we take inside a Amperian loop, okay, concentric with this system, then you see that there is no current passing through that. Okay, so the value of Bp will be equal to 0. The value of Bq is also equal to 0, but for a different reason. That in the first case there is no current enclosed. In this other case, when I have an Amperian loop like that, which I have shown over here, I'll just come back to this diagram, but the net current through it is equal to 0, because as many times the current is going in one direction, the same number of times the current is coming out of it, and therefore there shall not be any field outside of the toroid. Inside of the toroid, the field is considered as constant. Okay, the magnitude of the field is considered constant. Of course, the field keeps on changing as it goes like that, because it is in the tangential direction. Okay. Here, I have tried to make the toroid like this. Okay, the wires enter like this here, and they exit out of here, and they are very closely packed. So this pink and pink, these two circles, they show the section that I am talking about. And now I have taken one concentric circular Amperian loop, another one inside, and the third one outside. So here the point is P, here the point is Q, and here the point is S. Okay. So in the Amperian loop 1, as I said, there is no current enclosed. In the Amperian loop 3, this one, the bigger one, the dq is equal to 0, as the net current through it is equal to 0 for the reasons I have told before. Of course. Now what is of interest is the Amperian loop 2, where the radius of the loop is taken as equal to R2. So B dot dl will be equal to B dl. That is, along the Amperian path, dl and B are in the same direction, and therefore B dot dl will be equal to B dl cos of theta, which is equal to cos of theta is equal to 1. So B dl. So therefore I can write the contour integration about this contour, B dot dl is equal to B into 2 pi R2. Okay, because this is the length, this is the circumference of the Amperian loop number 2. So I can write B into 2 pi R2 is equal to mu naught into the total current, which is capital N into I. Right? I can write like this, mu naught N upon 2 pi R2 into I, where this N upon 2 pi R2 is equal to small n, which is the number of turns per unit length. So we obtain the same relation mu naught Ni, which we obtain in the case of a straight solenoid. So solenoid at toroid, the formula is the same, mu naught Ni, etc. Okay. So toroid schematics, and the schematics for that is appearing over there, and you can see for yourself that toroid as well as the straight solenoid is, of course, we get the magnetic field which is confined inside, which is equal to mu naught into Ni, where if naturally B is proportional to I, and B is also proportional to the number of turns per unit length. Okay. So you can even wind things like this, and then again go another way. So number of turns can be increased for the same tube on which the windings are done. Okay. I will just mention that this kind of an arrangement where we have a magnetic field, this can be used for the purposes of containing the plasma confinement. Because what is plasma? Plasma is an assembly of charged particles. If you don't want to lose those charged particles, then magnetic field is used, okay, which does not allow them to pass through what is known as the magnetic bottom. We'll have occasion to talk about that later on, but for now we have used the Ampere circuital law as an application to the case of solenoids and to the case of toroids. Okay. Next, we'll talk about the force between two infinitely long conductors carrying current, and there we will define basic property of ampere. And what is an ampere in the terms of what are the measurable things like force, etc. So the fundamental unit of electricity is ampere. It's not coulomb. Ampere is equal to coulomb per second. Okay. So coulomb becomes equal to ampere into second, because in the system that you have MKS and meter kilogram second, and then we had another thing, and that was Kelvin as temperature, and now we'll have ampere as the fundamental unit of electricity. So I have enjoyed, hope you have enjoyed, but please look at for these diagrams which are appearing. Thank you very much.